All right, good morning everyone. So, kumusta ang weekend? Sana nakapagpahinga kayo ng kahit konti. All right. So, and then no look now, it's middle of the week again. And Math 175 time na naman. Kaya lang ngayon, we will start with the brand new module. Mainit-init pa ito. Katatapos ko lang siyang isulat, I think, 2 a.m. Or 2 or 3 a.m. kanina, pero hindi ko pa natapos yung module 4. So this is just the first installment of module number 4. I'll just update the file later kasi I finally decided while I was finishing writing this section that I will discuss two more iterative schemes bago tayo pumunta sa accelerator methods next week. But before going into the details of these methods or the topic itself, some announcements. Na-announce ko na to sa D2L. So malamang na-marites na sa inyo yung kwento. So the institute is celebrating its anniversary as a National Center of Excellence in the Basic Sciences. So isang IMSP, I think sa pito sa buong Pilipinas that was created as a National Center of Excellence in the Basic Sciences by presidential decree. Pero you need to check kung 7 nga ba, but around that number, right? And only 3 of those were in UPLB, and IMSP is one of them. So we're very lucky to be part of this very nice and very um, very august institution. So, in line with this celebration, we are having some activities for which to which students are very much invited. So, on Monday, the 21st of March, we will be holding the Student Alumni Faculty Conference. So, meron mga magto-talk na mga alumni natin. Some, I think, at least one of them, or at least two of them, were also former faculty members to share their experience in the industry, right? And siguro how their training or how the training they got in the programs in IMSP helped them in their careers right now. So it will be great to hear from these alumni kung ano yung narating nila after doing an undergraduate work in math, applied math, or applied physics. Okay, so that's on Monday. So if you will attend, I will be giving you little incentives for the D2L, ano nga yung sabi ko? Problem set o ano ba? Lab exercise. Basta merong little bonuses para doon. Just write a half page or a one-page reaction paper or reflection paper about what do you think about the seminar, ano yung mga thoughts that came into your mind while attending that webinar, okay, or that online event. So yun, meron yung bonuses. And then on the 28th, that's Monday after next, we will have the IMSP research webinars, wherein all of the research clusters will be presenting some of the works that they were doing or that they were involved in the past few years. So para ipapakilala namin yung mga research clusters, and this will be very helpful for those who are still looking for the specialization or naghahanap kayo ng SP advisor. Ito yung magandang panahon para makita nyo ano yung mga topics na ginagawa ng bawat research cluster and who are the members of these research clusters para alam nyo kung sino yung lalapitan yung instructors. So I will also be giving bonuses dun sa mga attend, but I need from you sort of still a short write-up, but I want you to react on at least 2 research clusters. So because you guys, lalo na kung nag-SP na kayo or may majors na kayo, you might be biased to a certain research cluster na. So yeah, that's your interest. So kindly write about it. And siguro ikwento nyo kung involved kayo dun sa isa sa mga nabanggit na research endeavors ng cluster na yon, or kung aligned doon yung SP nyo or whatever, if you felt amazed by what they are doing and so on. But in the spirit of cross-disciplinarity, right, I want you to also pay attention to at least one more research cluster that might be different from your field of interest para makita nyo naman ano yung ginagawa ng mga ibang tao in the division. Kasi it is always nice to talk to other scientists, all right? Kasi halimbawa, tayong mga math, usually for a long time, especially in the 20th century. In the 20th century, parang we are resting on an ivory tower. We are looking down on everybody. lalo na yung mga pure math. So we are thinking that we are the queen of all sciences. So kayo yung lumapit sa amin, we are studying something elegant. Pero nagbabago yung paradigm ngayon kasi kailangan tayo yung bumaba dun sa pedestal natin and try to look for interesting problems in society, in the scientific community, kung saan pwede nating i-apply yung mga methods o yung mga theory na na-build natin. Kasi kung tayo lang yung nakakaintindi ng ginagawa natin, well, that's not fruitful knowledge, right? Knowledge will be stuck in the libraries and so on. But if we'll be able to share the knowledge that we have, halimbawa sa 175, natuto tayo ng root finding. Tapos sa mga examples natin, puro classroom problems lang, no? Mga made-up equations, made-up functions lamang. But it would be nice to say, talk to your engineering friends or talk to your friends from biosci or from even the natural science and the what you call this, the social sciences na baka meron silang problem na kailangan mag-solve ng isang nonlinear equation. Tapos hindi nila magawa by hand. At napaka-inefficient pag gumamit sila ng symbolic solver. So why not offer Newton-Raphson na mabilis naman yung convergence? So parang ganon, but in a larger sense. So when we become professionals or scientists, it will be great if we can share our knowledge to other people, offer our tools para ma-solve yung mga problems nila. And vice versa. Pero para makuha yun, kailangan natin ng open ears, alright? And the willingness to listen dun sa iba. Kasi minsan allergic tayo na, ayoko makipag-usap or makipag-collaborate sa mga engineers o sa mga physicists. Kasi kailangan kong pag-aralan yung physics nung ginagawa nila. Pero I think that's a little price to pay for the propagation of knowledge, right? Dami ko na namang nasabi, pero yun. And then there's another one. I just don't know the date, pero merong job fair. I think that would be the third or the fourth Monday from now. So kindly watch out for the announcements in our social media pages. So para naman kung graduating na kayo, naghahanap na kayo ng trabaho, so we have some companies coming over virtually. So para malaman nyo ano yung hinahanap nila, ano yung requirements nila, and who knows, you might land a job right there and then, right? And also that will also be beneficial to those who would be taking the practicum this mid-year. So probably pwede para magka-idea kayo ano yung mga companies na pwede ninyong lapitan pag naghahanap na kayo ng practicum. All right? So those are the lineup of events. Oh, by the way, disclaimer, dun sa job summit or job fair, hindi na ako magbibigay ng incentives kasi baka hindi naman lahat ay interested to go there, right? So you have two events that you can get incentives for. So, pero kailangan ko ng research, ng konting outputs, right? And then I'm a little bit strict on submission of bonuses. So, strict deadline na gagawin ko unless you will negotiate to me ahead of time. Ayoko yung sa end ng SEM na makikita nyo na tatawid ka na dun sa susunod na grade, pero kulang ka ng konting-konti tapos kaya siyang higitin ng incentive. So, and then I don't want to accept incentive papers dun sa dulo na. Kasi baka afterthought lang yun na, sige, gagawa na lang ako kasi pangtawid ko to sa susunod na grade level and medyo allergic ako sa ganun, right? So you do everything regardless of you have something definite in return from that. Of course, you will have incentives pero walang guarantee na makaka-apekto siya sa final grade. But I want you to do it hindi lang dahil kailangan nyo siyang gawin na pampataas ng grade, all right? But I want you to enjoy the process. Okay, so that being said, ano pa nga ba? Oh, I started grading, actually I finished grading yung mga submissions ng D2L for lab lab extra 1.2 part B. And some generic comments. Number one, please take note that the corollary 3.1 and the contraction mapping theorem are talking about fixed points. All right, magkaiba yung fixed points sa roots ng isang function. If you're talking about the same function, the fixed point of a certain function might be different from its roots. All right? Kasi pag sinabi mong fixed point ng isang function f, ibig sabihin nun, ito yung mga real numbers p such that f of p equals p. Yan yung definition ng fixed points ni function f. Ang mga roots naman ni f ay yung mga number r's such that f of r is equal to 0. So be careful when you write something, right? So hindi dahil nasanay tayo sa Newton-Raphson, sa secant method, na yung error estimates nila are talking about the roots of the function being considered, magiging careless na tayo pagsusulat when we're talking about the contraction mapping theorem. Sa contraction mapping theorem kasi, fixed points, right? So pati yung asymptotic error constant, nakadepende siya dun sa fixed point. Yung test for convergence of the fixed point iteration needs the derivative or the magnitude of the derivative at the fixed point of the function f and not at the root of the function f. All right? Doon nagko-coincide sila kasi meron tayong mga root finding problems na tina-transform natin into fixed point iterations. All right? So, naghahanap ako ng root ng isang function g. So, I'm looking for the function that satisfies this. Pero para makagawa ng isang fixed point iteration, kailangan ko itong i-convert into a process that looks like, say, x equals f of x. So, ito yung nangyayari na yung roots ni g ay posibleng maging fixed points ni f after some algebraic or simple manipulations. Okay? So, sana clear yon. Sa problem set, I will definitely ask you something about fixed points versus roots, and I'll be looking for a clear indication that you know the difference between them. Okay? Tapos just a minor comment, when you're checking if your solution is right for a particular equation, wag nyo nang gawin yung ganito. Halimbawa, x minus arctan x equals x. Yan yung chine-check nyo. Gusto nyo malaman kung yung resolve nyo na xi or na-solve nyo na p star is a good approximate to the solution of this equation. Pangit pala to. Dapat pala ito ay 1. Alright? So, yan yung equation. Gusto mo i-check yung na-solve or naibigay sa'yo nung fixed point iteration mo. Huwag na kayong mag-plug in both sides ng equation at the same time. So, halimbawa, ipa-plug in mo 1.1 minus arctan ng 1.1 equals 1. Huwag nyo nang gawin yan. Kasi when you write something like this in your work, if I will be reading it, and that's what I do. I read almost everything line by line. So pag binasa ko yan, etong proposition mo na yan, ibig sabihin kiniklaim mo na kagad na yung 1.1 minus arctangent of 1.1 is equal to 1, which doesn't look good. All right? Because the point of your exercise here is to check kung nasa-satisfy niya ba talaga. All right? So tanggalin na natin yung habit na nagwo-work ng both sides ng isang identity at the same time. You can do that if you're sure that this is true. Okay? Kung alam mo na totoo yung proposition na yan o yung equation na yan. But if you're checking whether this is true or you get a good approximation, then huwag nyo nang gawin yung nag-equate. Kasi pag binasa ko yan, ang interpretation ko na dyan, kinlaim nyo na equal siya talaga without proof. So what you need to do is to work with the two sides of the equation independently. All right? So magkaiwalay. So halimbawa, sa left side ka lang, mag-plug in ka dyan ng numbers. Tapos, carry out all calculations hanggang makarating ka sa isang number. Kasi ito yung i-compare mo dun sa result nung nasa right-hand side. Okay? So para lang hindi na kayo ma-minusan. Hindi naman yata ako nag-minus, pero probably when the problem set comes, I will definitely make deductions for little, ayoko siyang tawagin little, pero yung mga technical details na mga ganito, right? Little deductions lang naman, pero sayang din yung mga points. Okay? So I think that's all that I want to say before we start the discussion. So any reaction, comments? Okay, so if there are none, then let's start module number 4. As I've said, this is already available, but I will update it soon. Definitely before our next class on Friday. So this module is intended for this week, 14th to 18th of March. And then there will be a lab exercise 2. So that's going to be worth full 50 points. And that will be due on Monday. And it will depend on whatever we'll finish on Friday. But essentially, here's the thing that we want to do, all right? we want to implement Muller's and Bairstow's method in finding solutions to nonlinear equations, and you'll see later what's special about Muller's and Bairstow's methods. Bakit? Ano yung mga pagkukulang ng mga methods na na-discuss natin so far na kaya nilang i-address? Okay. We will also try to look at error bounds or estimates for these methods, but naghanap ako ng mga madadaling error bounds, but I think they're still too advanced for the course. And of course, since this is not just a programming course, this is an analysis course. So we'll also look at the pros and cons of these methods, and then the convergence as well on ng mga methods na to. And then of course, dahil gusto nating makita yung relevance ng ginagawa natin, we'll also try to use these methods to solve scientific problems. Okay? So here we go. More iterative methods. So, ano na nga ba yung meron tayo? Meron tayong interval methods, meron tayong iterative methods, specifically the Newton-Raphson method, which is very fast, the Secant method, which addresses some of the shortcomings of the Newton-Raphson, but at some cost, right? Medyo mabagal siya kaysa sa Newton-Raphson. And then we also have fixed point iterations, which is kind of a generic way of creating of solving for the roots of a nonlinear equation by defining a unique or very special fixed point iteration that will suit your purpose. Okay, pero common sa kanila, laging real number yung binibigay na approximate root. Okay, they always give us real numbers as estimates for the desired numbers. Okay, the iterative, the interval methods by design, real lang talaga yung kaya niyang ibigay. Kasi nangyayari sa interval-based methods, meron tayong interval AB, pinapalit lang natin siya ng pinapaliit hanggang ma-corner natin yung roots sa isang napakaliit na interval. Such that that interval is short enough that if we pick any number from that interval, we are sure that that number is within the desired distance from the actual root. And of course, there's no way that we can get away from the real number line in that scenario. Okay. And then dun naman sa mga iterative schemes, if you start with the real number as your initial estimate, then you are poised to always be to always get a real number. All right. Nandun yun sa pagkaka-design ng mga formulas dun sa mga methods na yun. If you start with the real x sub 0, you will end up with a real x star. Except possibly siguro sa fixed point iterations, pero wala tayong guarantee ng convergence for complex iterates. Okay? So, yun yung una nating ito-try na i-address today. Paano kapag gusto kong makuhang roots ay mga complex numbers, which is very usual in engineering and physics, even for math majors, kasi minsan naglalaplas transform tayo sa pagko-compute ng solutions ng ODEs or nagfo-Fourier transform para sa pag-solve ng solutions ng ODEs. Baka kailangan natin kunin yung mga non-zero root, yung mga non-real roots nung mga transforms na yon, right? They might be of value for our particular application. So really, complex roots are quite important. So there are several methods, but we'll talk about a very simple one, and this is called the Muller's method. You'll think that the idea is very simple, pero this method apparently was just introduced in 1956 by David Muller. Okay, so medyo bago-bago pa to, mathematically speaking, kasi it's wala pang 100 years since na-imbento itong Muller's method. But you will think that the idea is is a very natural extension of the secant method. Kasi ang ginagawa ng Muller's method ganito. Diba sa secant method, lagi tayong may dalawang estimate. So sige, drawing ako rito. Halimbawa, nandito ako sa interval AB, dyan ako naghahanap ng root. Ito yung function f. Okay. Tapos mag-start ako sa dalawang guesses. So say I'll have x0 here. And then I'll have x1 over here. The secant method will try to or will approximate the curve by the line passing through the function or the the points x0, comma f of x sub 0, and the point x sub 1, comma f of x sub 1. Okay. Kukunin niya yung line passing through these 2 points. And then the new guy, or the new x-intercept, will be our new estimate. This will be our x2. And that's how the secant method works. Okay? And it really works nicely kasi mataas din yung order of convergence nito, 1.618, the golden ratio. So, ganun kinukuha. Now, naisipan ni Muller na, okay, bakit ako ma-restrict doon sa paggamit ng straight line? Bakit hindi ko kaya siya gawing parabola? Bakit hindi parabola yung ipang estimate ko doon sa curve over a certain interval? However, maraming ways para gumawa ng parabola, right? That will approximate your curve. Pero ang kagandahan dun sa ginawa ni Muller, swak na swak ito para sa atin, kinuha niya yung interpolating quadratic polynomial dun sa para dun sa curve using 3 points. Alright, so remember interpolation theory, pag meron kang n plus 1 points, makakuha ka ng degree ng polynomial of degree not more than n that will interpolate the given function. Right? So yun yung naisip ni Muller. Kaya lang ang drawback nito, kailangan niya na ng 3 initial points. Okay? So kukuha siya ng 3 initial points. Halimbawa, ito. Ito yung x sub 2. So mag-start ka sa x sub 0, x sub 1, x sub 2. Kunin mo yung function value. Okay? Tapos, i-drawing mo, sorry, ang layo ng function value ko. Kukunin mo yung interpolating polynomial na dadaan doon sa 3 points na yan. Paano ko ba i-drawing yung parabola? Ang curvy kasi nito. Posible pa lang yung parabola ay ito. Okay. Dapat dumaan siya kasi interpolating polynomial. Palaking ko na lang yung point. But I hope you get the idea. So you start with 3 points, and then the unisolvence theorem from Math 174 tells us na pag meron kang 3 points, all right, makakuha ka ng unique interpolating polynomial of degree not more than 2. So we're hoping that pag nagkaroon tayo ng 3 points, makakuha tayo ng parabola. Tapos, of course, yung parabola na yan, magkakaroon siya ng at most 2 roots, right? Diba? Ito yung kompletong parabola. So, ang estimate natin para sa next iteration o yung bago nating x coming from Muller's method would be one of the roots of this parabola. So, either this one or this one. So, bayin nga natin yung kulay. Gawin kong green. Pwedeng ito or pwedeng ito. Pipiliin natin siya nicely. Ibibigay ko kami mamaya yung criterion kung paano napipili dun sa dalawa kung sino yung kukunin nating root. Okay? Yung kukunin nating bagong x sub I. But usually, we want that so that it would be closer to x sub 2. Siya yung mas malapit dun sa pinaka-previous na estimate. So in this case, this would be my x sub 3. And then you will do it again. But this time we'll do x1, x2, and x3. Kunin mo yung interpolating parabola for those 3 points. So forget about x sub 0 na update na yan. At every single time, we only deal with 3 points. So si x sub 3 na yung gagamitin natin. Okay? And we do this until some sort of halting criterion is met. Okay? We can either use jump-based a relative jump-based stopping criterion or a function value-based stopping criterion. And essentially, that's it. That's Muller's method. Ang simple-simple, di ba? Natural extension ng secant method. But I guess people already have some idea about it kasi parang ang odd na 1956 lang talaga ito na-invento. Siguro yung 1956, I'm betting that that's the only time that they were able to prove the convergence. Kasi sa secant method, madaling tanggapin na magko-converge siya. Kasi pagpalit na ng paliit yung interval, ibig sabihin palapit na ng palapit yung x sub n sa x sub n plus 1. Alright? Yung curve, so napakaliit ng pagitan nila. So yung straight line passing through the 2 points ay magiging approximately equal talaga dun sa curve. Kasi nga pag nag-zoom in ka sa isang curve, gano'n pa ka-crazy yung pagiging curvy niya. Alright? Para siya straight line. Basta nag-zoom in ka na sufficiently. Alright? So parang nagiging straight line na sila. So madali siyang tanggapin intuitively. Pero ito ay parang hindi naman ganun kadali yung convergence or hindi madaling maipakita yung convergence. Okay? But we'll talk about that later. But first, let's work out the math. This is the geometric picture, and I hope you understand the concept behind it. Pero yung pagko-compute ng math medyo kakaiba. Alright? Now, ito yung pinagpuyatan ko kagabi. Pwede ko kasi siyang kopyahin dun sa ibang books, alright? Meron silang formula, may usually Newton divided difference yung ginagamit nila kasi nagkaroon sila ng Newton form para dun sa interpolating polynomial. But I want to derive it in a more natural way for us para may continuity yung Math 174 and Math 175. At para ko konti na lang yung mga notations na kailangan kong i-introduce, alright? Kaya pag kinumpare nyo yung nasa modules natin kaysa dun sa makikita nyo sa Wikipedia or sa ibang books, wala ako ng mga symbols na F bracket, X0, X1, X2. Kasi hindi ko to diniscuss sa inyo sa 174. I discussed this siguro nung nag-174 ako noong 2014 or 2015. Pero tinanggal ko na siya sa outline kasi nasasayangan ako sa oras kasi kaparehas lang naman ng Lagrange form yung makukuha nyo using the Newton form. So, pero mas convenient kasi yung Newton form para sa Muller's method. But nevertheless, I worked out the math yesterday. Okay. Hindi pala yesterday, kanina. Alright. Medyo ang hirap niyang i-latex. So, kung papayag nga sana kayo, handwritten na lang yung notes para mas madali sa akin. Pero anyway. Right. So, meron pala ang figure 4.1. Ginanahan pala ako mag-drawing kahapon. Ito yung mas magandang drawing ng Muller's method. Okay. So again, we're fitting a parabola. Not just fitting, but we are using an interpolating parabola for the 3 points given at the initial stage. And then ina-update yung mga points na ginagamit by replacing the oldest, all right? Yung x sub 0, halimbawa, mawawala na siya sa susunod na iteration. Gagamitin mo na si x1, x2, at saka si x3, and so on. Okay? Now, paano mag-work yung math? Well, una, okay, kailangan natin ng 3 points. So, meron tayong points, saan ko siya sinulat? Yeah. Meron tayong 3 points, x sub 0, f of x sub 0, x1, f of x sub 1, x sub 2, f of x sub 2. So, given yan, 3 yung initial conditions. Tapos, ko-compute niyo yung function values. For brevity, isusulat ko yung f of x sabay na lang. Ayoko siyang i-type ng maraming parentheses pa ulit-ulit. Isulat ko na lang siya na f sabay. So f0 is f of x sub 0 hanggang f sub 2 ay equal kay f of x sub 2. So mga function values lang yung f sabays. Alright? Tapos, babalikan natin yung Lagrange form natin sa Math 174. Alright? Paano nga ba tayo nag-define ng interpolating polynomial? Kasi yun yung idea ni Muller. Kunin mo yung interpolating polynomial na dadaan dun sa 3 points dun sa iteration mo. Okay? So, a quick review of our notes then. Ito yung ibibigay niya. Formula 4.1. Yan yung formula para sa interpolating polynomial Q that will pass through the 3 points that we have. Okay? So, there's nothing new here, right? Tandaan nyo pa yan mula sa 174. Yung function value naka-multiply dun sa Lagrange basis polynomial. Okay? Tapos, syempre, tina-type ko siya sa latex. Ayokong mag-deal with this very complicated expression. So, sabi ko sa equation 4.2, sige nga, i-let ko na lang yan na ax squared plus bx plus c. Alright? So, para CA, ito na yung coefficient ni ax squared after I expanded everything. Okay? Tapos, with the aid of Mathematica, kasi syempre, ayoko namang mano-manong gawin ito, right? So, para i-expand yan na masulat sa form na ax squared plus bx plus c. Minatematika ko yan, ito pala yung coefficient ni x squared. Alright? So, nabigay sa equation 4.3. Ito yung coefficient ni coefficient ni x. Kasi ito yung constant term. Alright? So, essentially, the interpolating polynomial to our 3 points is this guy times x squared plus this guy times b plus the last guy. Yan yung itsura ng quadratic polynomial na magpa-pass through dun sa tatlong points na nabigay. Alright? So, sa program nyo, type nyo lang yung nasa equation 4.3. Okay? Alright. And then we're hoping that a is not equal to 0. Okay? If a is not equal to 0, everything would be fine. You will see later why. And then, ito yung isang, hindi ko pala nasulat, ito yung isang disadvantage ng Muller's method. Kapag si A ay nag-0. Kapag si A ay nag-0, problema tayo kasi hindi gagana yung quadratic formula. Siguro na-imagine nyo na kung para saan yung quadratic formula. At saka bakit ko siya sinulat na ax squared plus bx plus c. Alright? So, kapag yung initial points mo, yung initial guesses mo, ay naglalay sa isang line, yung interpolating polynomial will not be parabolic even if you use 3 points. Kasi ang sabi lang ng Unisolvent's theorem, there will exist a unique polynomial of degree not more than 2. Right? But if those three points will lie at the same line, or if there is a line that will pass through those 3 initial guesses that we have, then Lagrange or the interpolating polynomial will just be a linear function. And that means walang coefficients x squared, this guy will be 0. In that particular case, then your method or your iteration will be reduced just to be the secant method. Pero yung machinery na i-develop natin, hindi na siya gagana. Okay? Kasi magkakaproblema nga tayo dun sa root. Alright? Okay. So, yun yung little caveat dito. So, we are hoping that a is not equal to 0. And then remember, ang sabi ni Muller, ang piliin mong susunod na iterate ay yung x-intercept ng parabola na yon. We have the parabola, so all we need to do is to look for its x-intercepts. So for that, we will need to equate ax squared plus bx plus c to 0. Okay? So, yeah. Tapos wala naman tayong problema sa pagko-compute ng quadratic formula sa roots ng quadratic polynomials kasi meron tayong quadratic formula, right? So given the coefficients a, b, and c, we know that the roots of q are these 2 guys. Okay? So kaya sa program nyo, type nyo to kagad. So computing nyo si a, b, at saka si c sa taas para pagko-compute nyo ng roots, ay hindi nyo na itatype bawat isa sa kanila, right? So, yun din yung pandaraya ko kanina nung sinusulat ko ito. Yeah, kaya ako nag-ax squared plus bx plus c is not just to free myself up from the messy expressions here, but also so that I have to write a very long root. Okay? Okay, so ito yung quadratic formula. Kaya lang, I hope you have seen this in AMAT 152, or if not, dun sa lecture notes ng 174 chapter 1, I did mention there that the use of the quadratic formula might result to loss of significant digits. Isa to sa mga classic problem na pag gumamit ka ng quadratic formula, kapag ka nataon na yung A, B, and C have some are not very good for root finding, magkakaroon ka ng problema kasi posible magkaroon ng cancellation error. Alright? Or zeroing out of very small quantities. Lalo na kung mababa yung degree of precision or yung machine precision ng ginagamit mong computing device. Alright? So that's why when we are doing a machine implementation of the quadratic formula, we should stay away from this form. Okay. 4.5. And I suggest you guys use formula 4.5 instead of formula 4.4. But they're equivalent because this guy is just obtained by rationalizing the numerator of the right-hand side of equation 4.4. So mag-multiply ka lang dyan ng negative b minus plus radical b squared minus 4ac times the same thing. And this doesn't matter because that is just equal to 1. So pag kinary out mo yung multiplication na yan, ito yung makukuha nyo. Alright? So machine implementation will be better if equation 4.5 yung gagamitin nyo. Okay? So ito na, makukuha na natin si R plus, yung dalawang roots. Si R plus at saka si R minus. Okay? Now, we have a dilemma. Sino yung pipiliin ko? Si R plus o si R minus? Sige, David, bago yung dilemma.
Sir, question po. Bakit po nawawalan ng significant digits yung form ng quadratic formula na nasa taas?
Yeah, good question. So, sige, pahapyawan ko siya kung bakit. Well, because there is a possible kakaproblema ka kasi dito, dun sa numerator. Kasi posible na mag-zero out, okay, mag-zero out yung numerator, lalo na kung yung 4AC ay masyadong maliit. Though meron pa rin siya dito sa denominator, pero malalaman mo na nagkaroon ng problema kasi pag nag-zero yung denominator, magrereklamo yung computing device mo. Alright? Sabi niya, division by zero is not allowed. Pero kapag ka ito yung ginamit mo, alright? Kapag ka si b squared ay sobrang malapit kay 4AC, so, pag si 4AC ay masyadong malapit kay 0, so this guy, yung nasa loob ng radical, ay magiging b squared lang. Kasi pag sobrang liit nga ni 4AC, baka halimbawa 16 lang yung machine precision mo, tapos yung 4AC ay 10 to the negative 17, so talagang ititreat na siya ni computer mo to be 0. So magkakaroon ka na lang ng b squared dun sa radicand, tapos square root nun ay b, so magkakaroon ka ng negative b plus b, magzi-0 siya. So sasabihin sa'yo ng programming, nung software mo, r equals 0. Okay? Tapos hindi mo siya matitrace. Kasi there's nothing wrong with having r equals 0 unless later in your calculations you're going to use r equals 0 as r as a divisor. All right? Pero walang check para masabi na okay, pag nagkaroon ng loss of significant digits, hindi natin matatrack. Kasi nga, walang nangyayaring masama kapag magzi-zero to. Pero, tingnan niyo yung 4.5. Pag nangyari yung scenario na yon, ibig sabihin yung b squared minus 4ac, magiging malapit rin kay b. Magkakaroon ako ng negative b plus b. Magzi-zero yung denominator naman. Pero at this particular point, we will be notified na, hold on, there has been a loss of significant digits. Kasi nga, nagkaroon ng division by 0, especially if we are not expecting division by 0. Okay? So yung sagot talaga dun sa tanong ni David, nangyayari siya kapag ka yung 4AC ay malapit kay 0. Alright? Doon nagkakaroon ng loss of significant digits. Pero, kikita nyo later na, right, sa machine implementation, mas okay naman yung 4.5 talaga. Though there might still be a possibility of loss of significant digits in 4.5, pero ang mangyayari doon ay manonotify tayo. Alright? And then I think there's you can check the lecture notes I wrote for 174. Parang meron ako dong sinabi na division by a small number is not that prone to loss of significant digits. So kung ito ay napakaliit, okay lang yung division with it. Alright, so hindi siya nagkakaroon ng cancellation error. So yun yung mabilis na sagot dun sa tanong ni David. Okay? So any questions, follow-ups? Okay? So if none, then nandun tayo sa our na-compute na natin yung dalawang roots nung quadratic interpolant, right? So now we are to choose which among them will be chosen. Okay? So what we can do there is yeah, meron pa lang kailangang i-edit, sorry. May sinabi ako dito sa notes na gusto ko yung denominator ay maging maliit. Gusto ko yung denominator ay maging malaki. Tapos sa pag-isip-isip ko kanina habang nagkakape ako, parang mali yata yung sinabi ko na yun na dapat yung denominator ay mas malaki. I think the right way is to choose, dito ko na lang sulat, i-edit ko yung module later. So choose between R plus and R minus. So pipili tayo ng isa sa kanila so that x3, okay, pipili tayo ng isa sa kanila para maging x3 so that x3 is close to x2. Parang mali yung English. So, meron akong R plus at saka R minus. Pipiliin ko alin sa kanilang dalawa yung mas malapit kay x2. Alright? So, kailangan ko itong i-edit later. But essentially, yeah. Choose x3 to be the nearer to x2 between R plus and R minus. Alright? Kung sino yung mas malapit kay x2, siya yung piliin nyo na x3. Alright? So, yun yung maging idea. Never mind yung sinabi ko rito na eto, mali yan. Okay. So, kanina ko lang naalala. No time to edit na. So, yun. Piliin nyo yung x3 to be mas malapit doon sa x2. Alright? Between R plus and R minus. Okay? Now, bakit kaya nasabi na yung Muller's method can give us complex roots? Okay? And the reason there is very simple kasi nga meron tayong square root. Okay? So when we have a negative radicand, then that will give us complex numbers. And if you are working with a machine that understands complex arithmetic, then there would be no problem at all. All right? So kasi nga, di ba, yung quadratic, may mga quadratic functions na purely imaginary or purely non-real yung solutions nila. So yun yung nakaka-capture ng quadratic formula. So we are not discarding the possibility that the discriminant b squared minus 4ac is negative. Actually, we welcome it because that's the source for complex solutions. Okay? So that's one thing that you need to look out for. I-check nyo kung yung ginagamit yung software for the exercises admit complex arithmetic. Okay? Kailangan kasi yung complex arithmetic hindi lamang dun sa pagko-compute ng square root ng isang negative number, but also when one or more of your iterates become a complex number or a non-real number, posibleng yung b squared minus 4ac ay maging complex number. So kailangan marunong yung machine nyo to compute the square root of a complex number. All right? May convention sa pagko-compute ng square root ng complex number. Sige nga, let me see a show of hands. Sino yung mga nag 165 na? I think sa 165 lang yata dinidiscuss yung complex arithmetic. Meron na ba sa inyo nag 165? Hindi ko naman tatanungin kung tandaan nyo pa yung formula. Actually, hindi ko rin tanda yung formula. Kailangan nating i-derive pa para makuha yung square root ng a plus bi. Ang mga complex numbers. Wala pa nag 165. Okay, dahil wala pa nag 165, so kailangan tayong magtiwala. Tiwala dun sa ating computing software na kaya niya yung complex arithmetic. I can vouch for MATLAB, marunong siyang complex arithmetic kasi by default, ang structure niya ay complex. I'm sure Python can do that. I'm just not sure about Excel. So you need to be very careful if you're using Excel. Okay? And this might be a good time to migrate to MATLAB or Python kasi nga kailangan ng complex arithmetic. Okay? So, and I think that's it. Any questions about the method? Mangungutang uli ako hanggang 12:55 guys para ma-present ko yung examples. Questions? All right. So, kung wala, let's proceed to some examples. But I'll need to make a note here that by default, let's use the jump-based halting criterion for Muller's method. Okay? So meron ako dito example 4.1. Meron ako isang function x to the fifth minus 4x cubed plus x squared plus 3. Tapos gusto ko siyang gamitan ng Muller's method. Okay? So meron tatlong triples akong binigay. -3, 1, 2, -1, 0, 2, and -4 to -2i. So ito ay ordered triples. I mean, the first entry would be x sub 0, the next entry would be x sub 1, and the third entry would be x sub 2. Tapos i-implement natin yung Muller's method para dito. Okay? Disclaimer, i-double check ko yung mga tables na ipapresent ko ngayon kasi ginamit kong criterion dito ay palakihan ng denominator, CR plus at saka CR minus. Okay? But I just figured out there's something wrong with that. So dapat mas malapit kay x2. Now, the reason why we choose dapat mas malapit kay x2 ay para mapabilis yung convergence. But I think it's still fine whether you choose R plus or R minus. Okay? So magko-converge pa rin yung method, okay? If the initial guess is appropriate, okay? Magko-converge pa rin siya. Yun nga lang, kapag ka malayo yung x3 na pinili nyo mula kay x2, magtatagal siya. Alright? So, kaya siguro medyo matagal yung pag-converge ng ilang iterations ko kaninang umaga para sa Muller's kasi nga hindi maganda yung pagkapili ko ng x3. Alright? So, dapat si x3 pinili ko na lang kagad to be the mas malapit kay x2. Alright? So, I'll need to check some of the tables here, but the answers I think are fine. Okay? Medyo baka bumilis lang yung convergence. Okay? So, tinignan ko muna yung graph. It would be a nice practice to look at the graph of the function just to give us an idea ano yung problem na kinokompronta natin. Okay? So, here I ask Mathematica to sketch a graph of the function f. So, ito yung gusto ko sa graphing function ni Mathematica. Ini-scale niya na yung x at saka y-axis so that I'll get a nice window. All right? Though mathematically it doesn't make sense because look at 1 unit on the x-axis. 1 unit yan. Mas malaki pa siya sa 20 units dun sa y-axis. Pero the nice thing about that is we get the contours of the graph. We see how it behaves on a nice window. Kasi otherwise, isang malaking ganito lang siguro yung makikita natin kung same scale yung ginamit sa x at saka sa y-axis. And that's why labels are very important if your graph's scales are not the same. Okay, so ito yung graph ni function f. And what we see here is there is an asymptotic behavior going to negative infinity and negative infinity for extremely negative numbers and extremely positive numbers. Okay, and that is actually suggested. Actually, make sense natin yon kasi after some point, x to the fifth will dominate the rest of the terms. So, ibig sabihin, after some point, hindi na natin ine-expect na bababa yung graph sa kanan or tataas pa yung graph sa kaliwa. So, ibig sabihin, the roots that we are looking for actually are present in this window right away. And they are namely something near -2, something near 1, and something near 1.5. So yun yung tatlong roots na in-expect natin. Those are the 3 real roots which we might be able to get using the iterative schemes or the interval schemes that we have learned before. Alright? Pero meron pa nakatagong dalawa kasi sabi ng fundamental theorem of algebra, kapag ka meron kang polynomial of degree 5, which is our case here, meron kang at most 5 roots up to multiplicity, 5 complex roots up to multiplicity. So here, by looking at the graph, we are sure that we only have 3 real roots, so we have 2 complex roots missing, all right? Or the 2 missing roots must be complex. Or may multiplicity to yung mga roots, yung ilang roots natin dito, or multiplicity greater than 1, yung mga roots diyan. Pero in this particular case, I am sure we have 2 complex roots. Okay? So let's see if we will be able to get those complex roots. So first implementation, ginamit ko yung unang triple na sinabi, -3, 1, 2. Nirun ko yung Muller's program ko. Ito yung nakuha ko. Okay? And then complex number, real number, real number, real number. My first iterate is a real number kasi 0 yung imaginary part. Pero tingnan nyo yung x sub 4, meaning this is the result of the second iteration. Meron na akong complex na solution or meron na akong complex na estimate. All right? And then nanatili siyang complex for some time. Tapos dito, naging real na siya kasi naging almost zero na yung imaginary parts. So essentially, the initial condition or the initial guess that I used, -3, 1, 2, led me to the solution that is close to 1. Ito yung 1.20 na ine-expect natin kanina. Okay? And it's quite fast convergence kahit dumaan pa siya sa mga complex numbers because it only took 8 iterations for it to be done. Okay, and hindi siya katagalan, almost a little, wala pang isang segundo, natapos na yung computation niya. Okay, and the estimate that I get is this guy. Okay, pero tingnan niyo yung imaginary part niya. Yung imaginary part niya ay something times 10 to the -10. So that's very small, so you can just chalk it up as a real number. Sabihin mo, zero, almost zero naman yung imaginary number, and anyway, yung imaginary part, and anyway, we are really expecting a root that is close to 1.2. Right? So perhaps this is that guy. So yeah, eto na yun. Ayun yung nakuha kong estimate. Okay. And it gave me a very nice function value. So ang magnitude ng function value niya ay 10 to the -9, which is close to 0. All right. So I think we are successful with the initial guess -3, 1, 2. Okay. Now try to recreate this table, pero siguro antayin nyo na lang yung gagawin kong bagong tables kung may correction man dito sa Muller's sa module, all right? Kasi nga babaguhin ko yung criteria ko pag pili kanino kay R plus at R minus yung i-consider. But try to and then if I have corrected that, try to recreate the tables that I will include in the module. Okay. Now, second initial triple, -1, 0, 2. Pag -1, 0, 2 naman yung ginamit, ito naman yung magiging result. Okay? Yung nasa figure 4.4. I started with real initial guesses, but look at the first iteration. The first iteration birthed a non-real estimate na kagad. So imaginary na siya kagad, hindi na siya real kagad, tapos hanggang dulo na yan. Okay? Hanggang makuha ko ito, which is very close to the previous iterate. Kaya tumigil na ako kasi yung relative jump ay napakaliit na, 10 to the -11 na yung nangyayari. Okay. So here, I got -0.33 plus 0.76i, which is a complex root. Okay. Or which is our estimate for the complex root after 18 iterations. Okay. Now, just to check, kasi parang medyo may duda ako dito sa relative jump. Kasi yung relative jump, hindi siya consistently bumababa. Bumababa, tumataas, bumababa, tumataas. It's just that at the 20th iteration, or at x sub 20, all right, yung relative change from x sub 19 ay 10 to the -11 na. But I expect after that, liliit na ng liliit yung relative jump. All right? Pero medyo nagduda ako ng konti kasi before, parang ang bagal niya bago nagdi-decay yung relative jump. Ibig sabihin, all over the place yung pagpili ng susunod na iterate. And I guess I learned why. Ito yung naging indication sa akin kanina na may mali dun sa pagpili ko ng x sub 4. Kasi nga dapat ang pinipili ko ay yung mas malapit dun sa previous estimate. So ibig sabihin, there's a large relative jump here because maybe if this was R plus, the R minus, okay, siya yung mas malapit kay x sub 3. Siya dapat yung pinili ko. So mas napabilis sana yung convergence. All right? Pero ang kagandahan dun sa mistake ko sa dun sa pag-define ko ng method ay nakita ko na nagko-converge pa rin siya. Kaya lang mas matagal nga lang. I expect siguro in 8 iterations this would have been done if I chose x sub 3 to be the nearer between R plus and R minus to x sub 2. Okay? So yun yung magiging possible change dito. Pero since nagduda ako ng konti, kinuha ko yung function value nito. Pinlogin ko ito kay f, and what I got is a very small number. Dito na siya. Yeah. This is what I got. Okay. The real part is of order 10 to the negative 15. Oh, by the way, ang real part, siya yung, dapat pala sinabi ko kasi wala pa yata nagawa 155, no? Pag meron kang complex number na a plus bi, alright? Si a ay yung real part, tapos si b yung imaginary part, okay? So in this particular case, the real part is order 10 to the negative 15. The imaginary part is order 10 to the minus 16, almost to the machine precision. Usual machine precision kasi na default ay 10 to the negative 16. So when you see a number that is close to 10 to the negative 16, then that means as far as computers are concerned, 0 na yung mga yon. Okay? But of course, meron pa rin internal workings kung bakit nakakapag-manipulate pa rin tayo ng mga numbers na to. Yun na yung sa scientific notation, right? Yung floating point representation. But essentially, 10 to the negative 16, that is virtually 0. Okay? And then ang kagandahan pang isa dito sa example na to, nakapagbigay siya ng complex root. Pero merong isang theorem sa algebra. Yun yung tinatawag nating complex conjugate root theorem. Na kapag yung complex number a plus bi ay root ng isang polynomial. Alright? So take note, root ng polynomial. So kung siya ay root ng isang polynomial, then yung complex conjugate niya, yung conjugate, papalitan nyo lang yung sign nung imaginary part. So, ang conjugate ni a plus bi ay a minus bi. Alright? Yun ay laging solution din or laging root pa rin ng polynomial. So, complex roots always come in conjugate pairs insofar as polynomials are concerned. Okay? So, lagi silang magkakambal. So, nakuha ko na yung isang complex root, or we have an estimate for one of the complex roots, then I'll take the conjugate of it. So I'll just flip the sign of the imaginary part, and I'll get this. This guy is the second complex root that we are missing from the picture. Okay? And true enough, kapag pinlog in nyo to dun sa function f, what you'll get is a very small number again. A number that is virtually 0. Okay? May na kong typo. Okay, may question si Ezekiel. Bakit po biglang may 3 na whole number part ng estimate? Whereas dun sa iterations ay wala pong whole number part. Dito kasi Ezekiel ay nag-scientific notation ako sa pagdi-display ng results. So, it's negative 3 times 10 to the negative 1. Dito, dinisplay ko siya na floating point representation. Nag-switch nga pala ako nun kasi gusto ko kasi ay neat yung pagkaka-display dun sa command window. Pero pag nag-report na siya ng value, gusto ko ay scientific notation. Kasi pag halimbawa ito ay nag-plus 0.0000i, alright? So, makikita ko siya sa display. Pero pagka magre-report na ako ng final answer, gusto ko na ay scientific notation na para alam ko kung ano yung order. Alright? Katulad nun, halimbawa ito, pinakompute ko yung function value. Kung nag-stick ako sa floating point, baka ang i-output lang sa akin ni MATLAB 0.0000 plus 0.0000i. Pero hindi ko na makikita na 10 to the minus 16 or 10 to the minus 15 yun. Okay? So I think that's all the time I have for now. So siguro balikan natin to, itong example na to on mabilis on Friday, okay? And then I'll mention something about the convergence of the Muller's method. You will see na mas mabilis pa pala to sa Secant. All right? Thankfully, na-invento siya ni Muller at na-prove niya na mas mabilis ito sa Secant method pero mas mabagal ng kaunti sa Newton-Raphson. Kasi parang ang pinnacle na ng iterative schemes ay Newton-Raphson because it is very difficult to come by an iterative method that has quadratic convergence. Napakahirap na makahanap ng quadratically convergent na iterative scheme. And the secant, the Muller's method actually is quite surprisingly near quadratic. Ang order of convergence niya ay 1.84. Tapos nagkataon na mas mabilis pa pala siya sa secant. Alright? Ang secant kasi 1.61. ang rate of convergence ng Muller ay 1.84. Pero hindi na natin ipoprove. See, medyo komplikado yung proof, right? And probably that's the reason why this is formally accepted as an iterative method only in 1956. Okay? So on that note, meron ba mga pahabol na questions? On that note, let's call it a day. So thank you guys for joining me today. Enjoy the rest of the afternoon, and let's see each other on Friday. Okay? Bye, everyone.
Salamat po, sir.
All right, you're welcome. Pantay na lang ng correction siguro later tonight.